Students, welcome to RSET online classes for the course Analog Integrated Circuits. I am Assistant Professor Jasmin Sebastin from the Department of Applied Electronics and Instrumentation. The topic that we will be discussing in this session is active filters. This topic would be covered in 4 parts, of which this is the first part. In the first part, we would be discussing the basics of filters, what a filter is, what are the criteria based on which filters can be classified, what are the different types of filters, and some important terms in relation to filters. The upcoming parts of this session would cover the working, implementation, and design of active first order and second order, low pass, high pass, band pass, and band stop filters. So let us start the session. What is a filter? A filter can be defined as any circuit that inhibits the transfer of certain frequencies and allows only certain frequencies to pass through. That is, it has got a property of frequency selectivity. It can select the frequencies which the circuit wants to pass through and block or select the frequencies that the circuit wants to block. This property of the filter is called frequency selectivity. Now, what are the basic applications of a filter? Some of the most common and familiar applications of filter is in communication systems. We know that the receivers in our communication systems need to reject certain frequencies and receive and further process only certain desired signals. This can be implemented by using filters. Another familiar application is in DC power supplies to eliminate the high frequency noise at the AC input lines. Now, we studied the basic definition of filters. We will look into the classification of filters. Filters can be classified based on several criteria. One broad classification of filters is into analog and digital filters. Filters are classified into analog and digital based on the implementation technique. Digital filters are implemented using digital techniques and they use computers and some specialized digital hardware for their implementation. Whereas analog filters are implemented using components like resistors, capacitors, inductors, op-amps, and transistors. So, based on implementation techniques, filters can be classified into digital and analog filters can be further classified into passive filters and active filters. Passive filters are those class of analog filters which are implemented using passive components like resistors, capacitors, and inductors. The difference of active filters from passive filters is that in addition to these components like resistors, capacitors, and inductors, active filters also use active components like op-amps and transistors for their implementation. That is, active filters use both passive and active components for their implementation. So, we discussed the classification of filters based on their implementation techniques and components used for realization. Now, filters can be further classified into different types based on their frequency response. The types are low pass filter, high pass filter, band pass filter, and band stop or band reject filters. We will discuss each of these in detail and study the frequency response of these filters. Let us see what a low pass filter is. As the name indicates, a low pass filter allows only signals with frequencies lesser than a particular frequency to pass through. It blocks all signals whose frequency is greater than that particular frequency. The frequency below which the signals can be passed is called the cutoff frequency or critical frequency. the critical frequency can be decided by the person who designs the filter. So, we can define a low pass filter as a filter which allows signals with frequencies below the cutoff frequency or critical frequency to pass through and suppresses frequencies above the cutoff frequency. Let us see an example. Consider a low pass filter with cutoff frequency denoted by Fc. Let us consider three different input signals with frequencies F1, F2 and F3. Let the relationship between these three frequencies be F1 less than F2 less than the cutoff frequency Fc and F3 greater than the cutoff frequency Fc. Now from the definition of low pass filter, we know that a low pass filter allows signals with frequencies lesser than Fc to pass through, which means in this case, in the given example, only the signals with frequencies F1 and F2 are allowed to pass through this low pass filter. Since the frequency of the third signal F3 is greater than Fc, it will be blocked by the low pass filter. Now let us study the frequency response of low pass filter. What do you mean by frequency response? Frequency response plot, as we can see in the slide, is a plot of the gain versus frequency. The gain is mentioned in decibels and it is marked along the y-axis, and the frequency is marked along the x-axis. So from the frequency response, we can understand how the gain or the output of a filter varies with frequency. We can clearly see two graphs. One is that of an ideal low pass filter and the second is that of a practical low pass filter. We can see in the case of an ideal low pass filter that signals with frequencies lesser than the cutoff frequency Fc have a gain and is passed through, while after Fc, that is signals with frequencies greater than Fc, are not allowed to pass through. That is, it is suppressed. This region where the signal is allowed to pass is called the pass band, and the region where there is no signal or the signal is cut off is called the stop band. This is the case of an ideal filter, and you can see that the transition from the pass band to the stop band is very sharp or sudden at the critical frequency. That is, as soon as you reach the critical frequency, there is a sudden transition from pass band to stop band. But this is the case of an ideal filter and this cannot be realized in real. So in the case of a practical filter, we can see that the transition from the pass band to the stop band is gradual, or there is a small slope. It is not sudden. We can say that there is a gradual transition from the pass band to the stop band, and for a filter of order 1, the rate at which this transition occurs is 20 dB per decade, which means that for any decade change in frequency, the gain drops by 20 dB. We will discuss the fall of rate and order of the filter in the upcoming slides in detail. Now let us look at the second type of filter based on frequency response, and that is the high pass filter. A high pass filter is a filter which allows signals with frequencies above the cutoff frequency to pass through and suppresses signals below the cutoff frequency. So let us consider the previous example. Consider a high pass filter with cutoff frequency Fc and consider three signals with frequencies F1, F2 and F3. Let the relationship between these frequencies be F1 less than F2 less than the cutoff frequency Fc and F3 greater than Fc. We have defined a high pass filter such that it passes signals with frequencies greater than Fc. So here it is clear that only the third signal has a frequency greater than the cutoff frequency Fc. So we know that at the output we will get only the third signal with frequency F3. A high pass filter can be considered as a logical mirror of the low pass filter. As in the case of low pass filter, let us study the frequency response of high pass filter. We can see that for frequencies lesser than the cutoff frequency, there is no gain, or it is the stop band, and for frequencies greater than the cutoff frequency, we have got a gain. The region where there is a gain or there is a signal passed is called the pass band, and the region where there is no gain is called the stop band. As in the previous case, we can see that for an ideal high pass filter, the transition from stop band to pass band is very sharp or sudden. But that is not the case with a practical high pass filter. You can see that there is a slow transition from the stop band to the pass band, and this transition happens at a rate of 20 dB per decade for a filter of order 1. Next, we will look at the third type of filter based on frequency response, and that is the band pass filter. So, band pass filter allows only signals within a specified range to pass through. In the case of high pass filter and low pass filter, we defined one cutoff frequency. But in the case of band pass filter and band stop or band reject filter, we will have to define two cutoff frequencies. One is the lower cutoff frequency FCL, and the second is the upper cutoff frequency FCH. So a band pass filter is a filter which passes signals with frequencies between the lower cutoff frequency FCL and the upper cutoff frequency FCH. Let us consider an example wherein we have a band pass filter with lower cutoff frequency FCL and upper cutoff frequency FCH. Let us consider three input signals with frequencies F1, F2 and F3. Let the relationship between the frequencies be F1 less than the lower cutoff frequency FCL, which is less than the frequency of the second signal F2, less than the higher cutoff frequency FCH, which is less than F3. Now we know that a band pass filter allows only signals with frequencies between FCL and FCH to pass through, which means it is clear that out of these three input signals, this band pass signal with lower cutoff frequency FCL and upper cutoff frequency FCH will only let the second signal with frequency F2 to pass through. Let us look at the frequency response of a band pass filter. Let us look at both the ideal case as well as the practical case. We can see a difference between the frequency response of high pass, low pass and band pass filter. We can see that in the case of a band pass filter, we have two stop bands and a single pass band. And as in the previous cases, for the ideal band pass filter, the transition from stop band to pass band is very sharp or sudden. And similarly, at the higher cutoff frequency, the transition from pass band to stop band is also sudden. We have two stop bands and a single pass band between the lower cutoff frequency FCL and the upper cutoff frequency FCH for a band pass filter. Now, when we consider the practical band pass filter, again we see that we have two stop bands and a single pass band, and the transition from the first stop band to the pass band is not sharp, it is a slow transition, and the transition from the pass band to the stop band is again a slow transition. That is the difference between the frequency response of an ideal band pass filter and a practical band pass filter. This transition, as I said in the previous cases, happens at a rate of 20 dB per decade for a filter of order 1. By 20 dB per decade, we mean for any decade change in the frequency, the gain drops by 20 dB, in this case here at FCH, and the gain increases by 20 dB at FCL. Now let us discuss the fourth type of filter based on frequency response, band stop filter. A band stop filter is also called a band reject filter. As in the case of band pass filter, we need to have two cutoff frequencies for a band stop filter as well, FCL and FCH. And a band stop filter is defined as a filter which blocks all frequencies, signals with frequencies between FCL and FCH, and allows all other frequencies to pass through. Let us discuss this with an example. Consider a band stop filter designed with a lower cutoff frequency FCL and an upper cutoff frequency FCH. As in the previous examples, consider three signals with frequencies F1, F2 and F3. Let the relationship between the frequencies be as shown. F1 less than FCL less than F2 less than the upper cutoff frequency FCH less than F3. Now we know that a band stop filter suppresses signals whose frequencies fall between FCL and FCH and allows all other signals to pass through. So we know that in this example, the signal with frequency F2 falls between FCL and FCH, so that would be suppressed, and at the output we will get signals with frequencies F1 and also signal with frequency F2. Let us consider the frequency response of band stop filter as well. Here also we are considering the ideal case and the practical case. In the case of band stop filter or band reject filter, we can see that there are two pass bands, one lesser than FCL and the second pass band greater than FCH, and a single stop band between FCL and FCH. In the ideal case, we can see that the transition from the pass band to stop band at FCL and the transition from stop band to pass band at FCH is sharp or sudden. The difference between the frequency response of an ideal band stop filter and a practical band stop filter is that the transition between pass band and stop band is not sudden. There is a slow rate of transition. So, till now we discussed the different types of filters and the criteria based on which filters are classified. The first broad criteria is based on the implementation technique, and that is into analog and digital filters. Analog filters can be further classified based on the components that are used to realize those filters into passive and active. Passive analog filters utilize only passive components for their realization, whereas active analog filters utilize active components like op-amps or transistors in addition to passive components like resistors, capacitors and inductors for their realization. Then we discussed four basic classes of filters based on their frequency response. They are low pass, high pass, band pass and band stop filters. So all these four types of filters, low pass, high pass, band pass and band stop filters can be implemented using only passive components or using both active and passive components. Now let us do a comparison of active filters and passive filters. Active filters have several advantages over passive filters. Let us see these advantages one by one. One basic advantage of active filter over passive filter is that active filters do not exhibit insertion loss. That is, there is no loss in the pass band when you implement an active filter. Whereas when you use a passive filter, there would be a loss or a drop in gain in the pass band. One major advantage of active filter over passive filter is that you can design an active filter to provide a gain if you wish. That is, when you design an active filter using an op-amp, you can design it in such a way that it can provide a gain but this is not possible in the case of passive filters. In the upcoming parts of this session, when you learn more about active first order and second order filters, you will learn how to design active filters with different gain. Another major advantage is that active filters do not have the problem of loading the source or the load. That is, consider the case where you implement an active filter using an op-amp. The basic feature of an op-amp is that it has got a very high impedance at the input, which is ideally infinity, and a very low impedance at the output, which is ideally 0. So because of this high input impedance, when you use an op-amp to implement an active filter, it avoids loading the source. And because of the very low output impedance of the op-amp, it avoids loading of the load. So this is not possible with passive filters. This is an advantage of active filters. Another advantage is that active filters are more economical than passive filters. You can have a wide range of op-amps which are very cheap, and in addition to that, the active filters using op-amp have the above listed advantages. So you can say that active filters are way more economical than passive filters. Having said all this, it does not mean that active filters are perfect or they do not have any disadvantages. Active filters do have some disadvantages when compared to passive filters. We know that for an op-amp to operate, it has to be given a DC power supply. So if you implement an active filter using an op-amp, then for the proper operation of the filter circuit, you need to have a DC power supply. This is not required in the case of a passive filter. Also, the frequency of operation of an active filter is limited. This is because an op-amp has got a finite gain bandwidth product, and so the frequency of operation or the range of frequencies is limited for an active filter implemented using an op-amp. Another disadvantage of active filters is that it does not have the capability to handle large amount of power. That is, active filters are generally low signal level circuits. So till now we discussed classification of filters based on implementation techniques and their frequency response. There is another classification based on the nature of the frequency response. We know that for an ideal filter, we expect a flat pass band and a flat stop band and a sudden transition from the pass band to stop band. That is, there should be no ripples in the pass band or the stop band, and at the cutoff frequency, the transition should be sudden from pass band to stop band or vice versa. So there are several filters which satisfy some of these characteristics, if not all. So some of the filter types are Butterworth, Chebyshev, elliptical and Bessel filters. Each of these filter types have different characteristics, which we will see in the upcoming slides. But for our session, we will be focusing only on Butterworth filters. We will be learning the design and implementation of only Butterworth filters. This is the frequency response of a Butterworth filter. We can see that we have a flat response at the pass band as well as at the stop band. That is, the response of the Butterworth filter is devoid of any ripples in the pass band as well as in the stop band. Because of this type of nature of response, a Butterworth filter is also called a maximally flat filter. In the previous slide, we discussed about other filter types such as Chebyshev, elliptical and Bessel. We will just see the frequency response of Chebyshev filter to understand the difference in characteristics between these filter types. Chebyshev filters are of two types, type 1 and type 2. We can clearly see the difference in the frequency response between Butterworth filter and Chebyshev filter of type 1. We can clearly see from the frequency response that there are ripples in the pass band of Chebyshev filter of type 1. But the transition from the pass band to the stop band is comparatively quicker when compared to the Butterworth filter. Now I said Chebyshev filters are of two types, type 1 and type 2. Let us see the frequency response of Chebyshev filter of type 2. We can see that the pass band has got a flat response, whereas there are some ripples in the stop band. The transition from pass band to stop band is steeper when you compare it with Butterworth filters. So this is the basic difference in characteristics of Butterworth and Chebyshev filters, and we will be focusing more on Butterworth filters in our upcoming sessions. Now in the previous slides when we discussed the frequency response of low pass, high pass, band pass and band stop filters, we mentioned a term called order of a filter. We said that the fall off rate from or the transition rate from pass band to stop band or vice versa happens at a rate of 20 dB per decade, and that is for a filter of order 1. Now what do you mean by order of a filter? Order of a filter indicates the number of delay elements in the filter circuit. By delay elements we mean the RC stages in the filter circuit. If we have a single RC stage in a filter, the filter is of order 1. If we have two RC stages in our filter, we can say that the filter is of order 2. And we said a filter of order 1 has a fall off rate of 20 dB per decade. Now what do you mean by this? We'll try to understand with a figure. This is the frequency response plot of a low pass Butterworth filter. We have drawn two plots here with two fall off rates. The red line indicates a filter of order 1 with a fall off rate of 20 dB per decade. Let us consider 2 points, frequency f and a frequency 10f, which means that there is a decade change in the frequencies. Let the gain at frequency f be A1 and the gain at frequency 10f be A2. So it means that by 20 dB per decade fall off rate, we mean that when the frequency changes by a decade, the fall in gain is by 20 dB. That is, when frequency changes from f to 10f, the gain drops from A1 to A2 and the difference between A1 and A2 is 20 dB. That is what we mean by 20 dB per decade. And the fall off rate is 20 dB per decade for a filter of order 1. That is, you have a single RC stage in your filter. It is called a filter of order 1. Now consider a filter of order 2. That is, you have two RC stages in your filter circuit, and we discussed that a filter of order 2 has a fall off rate of 40 dB per decade. Let us try to understand that with a figure. The same figure, we said that the blue curve indicates a filter frequency response of a filter of order 2. Let us consider two frequencies, f and a frequency 10f, and let the gain at f be A1 and the gain at 10f be A2. Consider the blue curve with that is the frequency response of a filter of order 2. Now there is a decade change in frequency, that is, the frequency changes from f to 10f. So at the same, and while this happens, the gain changes from A1 to A2, and the difference between A1 and A2 would be 40 dB. That is what you mean by a filter of order 2 has a fall off rate of 40 dB per decade. From this we can understand that as the order of the filter increases, the fall off rate is also faster. So it means that as you keep on increasing the order of the filter, the transition from pass band to stop band becomes quicker and the response of the filter approaches the ideal response. we can see that in this figure, as the filter order increases from 1 to 10, the transition from the pass band to the stop band becomes steeper or sudden, and the response approaches the response of an ideal filter. With that, we have come to an end of this session. We'll just have a quick recap. In this session, we introduced filters, we defined what a filter is, we discussed about the different criteria based on which filters are classified, the different classes of filters, we studied what frequency response means, we studied the frequency response of low pass, high pass, band pass and band stop filters, we introduced Butterworth filters, we introduced and understood the term order of a filter, and we saw how the frequency response of a filter approaches the frequency response of an ideal filter as the order increases. In the upcoming parts of this session, we will study the design and implementation of first order and second order, active, low pass, high pass, band pass and band stop Butterworth filters. Thank you.